Today we're going to be talking a little bit about buffers. Again, a little bit of review from hopefully Chem 1. Buffers are really good solutions. Basically, they help so that the pH isn't such a dramatic change when we add acid to something. So for example, if we add 1 milliliter of 0.1 molar hydrochloric acid, which is not that concentrated, to 1 liter of pure water, so think about how much smaller 1 milliliter is compared to 1 liter, the pH of that solution changes from 7, neutral, to 4, very acidic. So this is a 1,000-fold increase in acidity of the solution, even though we only added a small amount of that acid. So that's a dramatic change. A lot of times it's nice to have a solution that doesn't change so dramatically when such a small amount of acid or base is added to them. For example, your blood has buffers in it to avoid these changes and to maintain homeostasis in your body. If the pH of your blood was changing that drastically, it would not be good. So your body produces these buffers to resist that change. A buffer, one definition, is a solution of weak acid or base and its salt. So a salt containing a similar ion to a weak acid or a weak base. Both components have to be present to resist a change in pH, so you can't just have a salt or the weak acid or base, you have to have both together. So some common buffer examples are the acetic acid, which is vinegar, a weak acid, and the acetate ion. This acetate ion, for it to be a salt, could have been bound to, for example, sodium, Na+, or any other group 1 metal, maybe a group 2 metal. You want this to be a soluble salt. Typically group 1 metals are very soluble when bound to an ion in a salt. Another example would be carbonic acid and the hydrogen carbonate ion. So the acid has another H versus just the ion, which is HCO3. So the way that buffers work, first we're going to talk about when adding acid, how it resists that pH change. So the pH of a buffer containing 0.5 molar CH3COOH, which is carbonic acid or acetic acid, and 0.5 molar of sodium acetate is 4.74. If 10 mils, which is much more than the 1 mil, of 1 molar, more concentrated, HCl is added to 1 liter of this buffer, the pH only decreases to 4.73. So not a big change at all, even though we're adding much more and more concentrated acid. So with the weak acid, this is the equation essentially that the weak acid is experiencing in a solution. So when you add a weak acid to a solution, it typically breaks into H plus and CH3COO minus. And typically this is a reversible reaction, so it does go both ways. But what's important that you should notice is that the weak acid and the ion of its salt is present on opposite sides of this equation. The other thing that's important is this H right here. So we will be talking about rates of reactions later on in the year from Chem 1. Hopefully you remember this. But typically if you add either a product or a reactant to a solution, so if you have this equation here, if you add more H+, that's going to make the chemical reaction proceed this way so that more of this is produced, ultimately reducing the amount of H+ in the solution. So it has to do with reaction rates. So when an acid is added, the ratio of weak acid and salt that are present in the buffer change relative to one another. So one increases while the other decreases, or vice versa. This reaction is basically a side reaction that essentially soaks up some of the H+ ions from the acid to reduce the change in pH when an acid is added. So when we have just this in a solution and then we add HCl, HCl is a strong acid that is going to break up into H+ and Cl-. That H+ can be taken up by any of these salt ions that are present in that solution to produce more weak acid, which don't affect the pH nearly as much as the strong acid does. Okay, so when we add H+, some of the salt reacts, so we have less of this ion in solution and more of this acid, but the pH stays relatively close to what it originally was. When we add a base, so instead of adding a strong acid, this time we're adding a strong base, sodium hydroxide. This is the reaction that occurs. Again, what you should notice is that we have the acid on one side of the equation, the weak acid, and the ion salt on the other side of the equation. So again, these two can change relative to one another. What happens in this reaction, this side reaction, is that the H from the weak acid will bind with the OH- provided by the strong base to create water and the salt. So again, if we are adding NaOH, it is a strong base, so it's going to break up into Na plus and OH-, and then this reaction can occur. Some of the weak acid from our buffer solution is going to react or take up that OH- to create more of the salt and some liquid water, which has a neutral pH. So again, here, the pH is only changing to 4.76. Again, not a big change at all. So buffers essentially soak up hydroxide or hydrogen ions. When they soak up, what's happening is a side reaction that basically occupies those so that the pH does not change drastically. There is something called buffer capacity. So buffers do not work, I don't want to say forever, but for any given amount of acid and base added. So if you keep adding acid, eventually the buffer can't do much. Or if you keep adding a base, eventually the buffer cannot do much. So it can only resist changes in pH for so long, meaning it can only resist changes in pH for so much acid or base that you add. The buffer capacity is the amount of acid or base that can be added before a large change in pH occurs. So the capacity is exceeded when the number of moles of H+ or OH- ions that are added to the buffer exceeds the number of moles of the buffer components. So going back to the base, this will only work as long as we have these acid molecules in the solution. Eventually, we run out of these acid molecules to actually react with the base to neutralize the solution. With the acid, we only have so much of the salt ions in the solution. Eventually, we run out of these salt ions that can no longer occupy these H+ to change or resist change in the pH. So eventually H+ are added to the overall system, which is going to result in a dramatic change in the pH of the solution. Okay, so that's a little bit about buffers. Typically in AP Chem, all you have to do is be able to identify a buffer. So you have to basically identify that it has a weak acid or a weak base and the salt of that weak acid or weak base. Okay, let me know if you have any questions. Again, we will be going into more detail with these later in the year. This is just like an introduction that I would have given in an introduction chemistry course. Yeah, let me know if you have any questions.